We'll be showing you how to analyze crystal structures using Mercury before you get to try some examples in our hands-on exercises with tutors online to help you. We'll finish by exploring more advanced tips and tricks and see what we've learned together in a fun quiz. We will be recording this session, so if you don't want to appear on camera, now's your chance to turn your camera off. By the end of the session, we'll be able to use the Mercury Calculate menu to explore structures in more depth. We'll look at contacts, planes and centroids, as well as discovering tools in the display menu, including symmetry elements and voids. So some things you need to know for today. As we mentioned, we'll be recording this session, but we will turn off the recording during the hands-on part, so you can ask us lots of questions during that part. If you have a question during the presentation or demo, then you can type these in the chat box at any time, and we will try and answer as many as possible. So we will get familiar with the chat box, then now's the time to open it up and to tell us where you're joining from. So you should see the little speech bubble icon at the top of your Teams window. So if you can all go there, tell us who you are and where you're joining from. While you're doing that, just cover what you need for the hands-on part. So you'll need Mercury installed with an active CSD license and the workshop handout you should have received earlier this week on Monday. If you don't have Mercury installed, you're not going to have time to install all our lovely software and data before the hands-on part, but you can still follow our presentation and demo and then try the hands-on part later. We've got a few people joining from the UK. Please do tell us where else you're joining from. Somebody joining from Germany, South Africa, Belgium. It's very global so far. So we're finding out a bit more about you. Let's introduce who your hosts are for today. So I'm Susanna and I'm joined today by your tutors. So we've got Ilaria, our Education and Outreach Officer. We've got Natalie, our Data Integrity Research Scientist. And we've got Alex and Andy, two of our Research Application Scientists. So as well as finding out where you're joining from, and I can see South Africa, Germany, Spain, Netherlands, more from the UK, Italy, we want to find out a little bit more about you. So you should, in a couple of seconds, see a poll on your screen so you can tell us if you have attended a virtual workshop before. So you should start to see the form now. So we want to know, have you attended a virtual workshop? Have you visualized a structure using Mercury? Have you analyzed structures? Have you collected or refined your own crystal structure? Or have you deposited a structure, or none of the above? So we're starting to see some coming in. So a lot of you have visualized structures before.
Sí, ese.
Okay, so it looks like most of you are getting some responses. Most of you have visualized structures. We'll just give you a few more seconds to fill in before we go to the next bit. And there's a few newbies as well. Okay, so we will close the poll, and before we explore and analyse structures in the Cambridge Structural Database, let's start with a quick reminder of what's in the CSD. So it was established in 1965 and it contains over 1.1 million structures. It includes every published organic and metal organic structure, and including data associated with scientific articles, patents, repositories, thesis publications, or published directly through the CSD as a CSD communication. It's really a community effort, so structures are determined by crystallographers worldwide, and every single entry is enriched and annotated by experts to aid the discoverability of both data and knowledge from the resource. And you can see the growth of the CSD here, and one of the structures in the repository known as Kitten. So hopefully we all remember what Kitten is. So as well as being a cute cat, it is a CSD ref code, which is our database reference code containing 6 to 8 characters. It's used to identify entries in the CSD. Structures of the same substance are assigned the same 6-letter code with an additional 2 numbers, and they are collected together in what we call a ref code family. Today we'll be journeying through some of the structures in the CSD, and along the way we may spot some more familiar sounding ref codes, such as Ginger, Catman, Nelson or Donkey. So if you have a favourite ref code too, then do let us know in the chat again. So as I'm sure you know, the CSD contains a mix of organic and metal organic structures with a split between single and multi-component complexes. It's used in a variety of industries, including pharmaceutical and agrochemical, and it can also be used to understand fundamental bonding. As well as more experimental data, such as melting point, crystal colour, crystal shape, the CSD entry includes key crystallographic information such as unit cell and crystal space group. So let's use space group to see one of the ways that the structures in the CSD have changed over the last 50 plus years. On our left-hand side, we can see what space group structures published between 1965 and 1970 were determined in. And this is compared to our graphic on the right-hand side that's looking between 2015 and 2020. So you can see that P21 over C is a very common space group, and back when the CSD was first established, that was followed by P21, 21, 21, and then P bar 1. And today it's P21 over C, followed by P bar 1. So now we've reminded ourselves of what's in the CSD, we want to find out a bit more information about you. So you should see our second poll of today, and asking what kind of structures you're interested in analysing and what aspects of structures do you want to explore the most. So you should have those 2 questions on MS Teams now. So are you interested in analysing organics, metal organics, inorganics or proteins? And what are you most interested in exploring? Symmetry, planes, centroids, hydrogen bonded networks, or other? So I can see a lot of you are interested in hydrogen bonded networks. A lot of you are, I think it's a split between organics and metal organics. So we've just learned that the CSD contains organic and metal organic structures, so that's a good sign. And if there are other things that you'd like to learn and you want to type those in the chat box, I can see that 13% of you have ticked other, then do type those in the chat box as we go through the session. Okay, so we're now going to look at some of the software that goes alongside the CSD and the CSD portfolio. So to help us get the most out of the data in our database, we have a range of associated software to help us search, visualize, analyze, and learn from the data. Today, we'll be using Mercury in CSD Core to analyze structures in more depth. So with Mercury, you can explore crystal structures, you can generate high quality images, create 3D printing files, and you can analyze geometries, interactions, and packing inside the structures. In our Mercury for Beginners CCDC virtual workshop that we held last year, we learned some of the basics of the Mercury interface, how to pack structures, and we created some high resolution publication ready images. So today we're going to be building on that knowledge to learn more about the structures and more analysis of those structures. So we're going to move on to our show one section. So if you want to follow along, you can open Mercury now by clicking on the Mercury logo on your desktop or navigating to Mercury in your program menu. By clicking on this icon, you will open the Mercury interface that we can see here. Just a reminder, there are a number of ways you can use the mouse to move, rotate and zoom, and these instructions are all in your handout. We will also use the structure navigator on the right hand side to view any one of the 1.1 million structures, so including kitten or your favourite ref code. You can just type it there. There's a few other ways to use your mouse, including in combination with the keyboard, and you can also right click on the structure visualizer to see additional menus. So again, all these instructions are in your handout. As well as using the mouse, we can also change which toolbars we see, and you can do that by going to display and toolbars. So if we accidentally close our ref code list, known as the structure navigator, we can add it back just by ticking structure navigator. Another useful button to remember is the reset button. So that's at the bottom left, and that allows us to reset our Mercury view. So now the reminders are out of the way, let's explore the menus and see what we saw last time and what we'll learn about today. So in total, there are 11 different menus to discover, starting with File, Edit and Selection. So you can now click through them and re-familiarise yourselves with what's inside them. Today, we'll be mainly exploring the Display menu and the Calculate menu. But there are lots of other menus to explore, including free tools and services in CSD Community, our core system tools in CSD Core, including Mogul Geometry Check, which we'll see later, and more advanced tools in CSD Materials and CSD Discovery. And before we finish today, we'll also take a look at how we can use the CSD Python API to programmatically access the CSD portfolio. So now we know about the menus, let's think about why we might want to analyse structural data. So as we saw in our beginner session, the ability to visualise molecules and structures in 3D can be really powerful to help us to understand key chemical and crystallographic concepts. By understanding intermolecular interactions and crystal packing in structures, it can also help us to design new solids with desired physical and chemical properties. This can be particularly helpful when exploring different polymorphic forms and when thinking about what impacts the stability of a crystal. So there are a number of different characteristics that influence crystal stability, and we'll be looking at some of these today, such as hydrogen bonding and symmetry. So let's start by looking at contacts. Hydrogen bonds and short contacts can help to stabilize a crystal structure, and so they can help us to understand why structures or different polymorphs have different properties. So perhaps we could use them to understand why different polymorphs of chocolate exhibit different physical properties and why chocolate can sometimes lose its snap. Let's look at a more serious example, and the one that you can see here. So in the 1990s, a marketed HIV drug suddenly changed polymorph to an undesirable form. This new form had different therapeutic properties and had serious consequences for the pharma company involved, who had to quickly withdraw the drug, but more importantly for the patients who relied on that drug for treatment. So if we look at the two different forms, we can see they have different hydrogen bonding networks. And by better understanding the hydrogen bonding networks within the crystal and learning from the wealth of data in the CSD, we can now better mitigate the risk of this ever happening again. So hydrogen bonds are frequently observed in organic structures. They have been studied for around a century. And when investigating hydrogen bonds, we need to know what defines one and when a bond changes from a van der Waals contact to a hydrogen bond. Of course, all of this information could be found in a textbook, it could be looked up on Google, or we could look at it in the glossary in our handout. But with the CSD, we can actually delve further and see what's happening for ourselves. We can, in effect, endeavour to look for them and look at them, and then we can actually learn from them and learn from what we see. So if you want to follow along, we are going to navigate to hexacan. So we're going to type HXACAN in our structure navigator ref code and click find. This is a paracetamol structure. And to look at the hydrogen bonds, we're going to tick H bond here and we're going to show hydrogens. By clicking on the default definition, we can change what we define as a hydrogen bond. So we get to see this pop up. So why not change some of these options and see, we'll be recording this session. Forget to click back to default before continuing to follow along. If you have a question, we can expand our hydrogen bond network by clicking or left clicking on the atoms at the end of the dashed line. So these atoms here, and these are known as hanging contacts. And just click to your hosts are for today. So I'm a research scientist, and we have more advanced options, including how to remove the hanging contact from our display. Mercury, have you analysed? So we're starting to. The contacts quite hard to see, so we can change the thickness of our contact by going to display, styles, contact settings, and then we can change the default radius. So you can see I've made it thicker. Or we can change the color of our high reference code containing 6 to 8 characters using a color code based on the donor acceptor distance. If you have a favorite ref code too, colors, contacts, and then we're going to select color by distance and apply to all contacts. So if you're following along, you should now see something more like this in your Mercury window with a different color coded that's looking between. If we want to measure the distance of our hydrogen bonds, we go to picking mode. So we're going to change the picking mode to measure distance and then click on atoms we want to measure the distance between. So I can start to build up a better picture of my hydrogen bonded network. Good sign. From our last session, you can change the position, size and color of the distance labels as well. So you can find these instructions in your handout as well. If you want to explore the contacts in more detail, then we can click on more info along the bottom and select contact list. So we now get this pop-up where we can see our hydrogen bonded contacts listed with additional information. So in the all these instructions are in your handout. A number of ways to expand contacts or change definitions. And you can find some of these by going to calculate, through them and re-familiar pop-ups. You can find the contacts. You can expand the contact network. You can change the definition to visualize molecules and structure and decide whether or not to show intermolecular or intramolecular bonds. So for our hexacan structure, we're just going to click on some of the other hanging contacts, a bit different physical properties and might work to get a better picture of what it looks like. So if we were now rotate the structure, we should be able to see if it's a 1D, 2D or 3D bonded network. So in this case, we can see that we've got a 2-dimensional sheet. But what you could do is explore some of the other polymorphs or structures in the same ref code family to see what other types of networks you can find. So to analyze the hydrogen bond network in more detail, we can use graph sets, which are used to describe hydrogen bonded patterns. So to do this, we can go to calculate and then graph set, and then we'll see this pop up, my hydrogen bonded network. through the different descriptors to see the different patterns. So here you can see a graph set pattern that's got a ring of 4 different molecules and 22 different atoms within that ring. If I click to another graph set, just now rotate the structure with 6 different molecules with 40 different atoms. So not every structure is going to have hydrogen bond donors or acceptors, or we may want to look at other stabilizing interactions such as short contacts. To do this, instead of turning on hydrogen bonds, we can turn on short contacts, which you can see also includes the hydrogen bonds we saw earlier. And we can use a lot of the same menus that we saw for hydrogen bonds to explore the short contacts as well. So you can see some of the menus here. So now we've seen hydrogen bonds and short contact networks, how else could we analyse how the molecules are arranged in the crystal? So what we could look at is coordination sphere of a molecule using what we call molecular shells. To do this, we go to Calculate and Molecular Shells. And in this case, I've selected one of the molecules, and you can see how many other molecules surround our selected molecule in the crystal structure. Instead of molecular shells, we could also decide to create a centroid. So a centroid is a geometric centre of a group of selected atoms. So we can then see how similar centroids are arranged in a crystal. So in our hexagon example, we're going to reset the view and then turn packing on and navigate to the Calculate Centroids menu and then New Centroid. And in this case, I'm going to construct a centroid from the ring. So by selecting ring and then one of the atoms in my benzene ring here. So I can now see my centroid and I can start to add centroids for all of the rings in the unit cell. And now I've got my centroids, I want to see what some of the distance, angles and torsions are between my centroids. So I can do that by again changing the picking mode. And in this case, I've changed the picking mode to distance, and I can start to measure the distances between my centroids. If I want to clear the centroids, I can right-click on the centroid to bring up the object menu, and then I can delete the objects or clear the objects. Another object we can create to explore crystal packing is a plane. So I'm going to reset my view again, turn on packing, and then go to Calculate Planes. And again, I see a similar pop-up. I'm going to create a new plane, select a ring, and again, pick one of the atoms in the ring. I can change the color of my plane, and I can also set the plane to be transparent so I can see through the plane. So here you can see 2 different ring planes and how they dissect each other. So we've looked at some of the ways we can explore the arrangement of molecules in a crystal, but as crystallographers, we know that crystal symmetry is important as well. It enables us to describe an entire crystal structure without determining every atomic position. And just like contacts, symmetry can impact the physical characteristics of a crystal. So it can help to understand differences between structures and between polymorphs. Incorrect crystal symmetry can also lead to impossible or difficult to solve structure determinations. And we know that a number of structures in the CSD have actually subsequently been reassigned to a higher space group. So by visualizing symmetry in the 3D, it can help us to better understand how crystal symmetry works, and we can see a more visual representation of the international tables for crystallography. So let's look at how we can do that in Mercury. So we're using the same structure, and we've got packing turned on, and I've hit reset to get rid of all my previous planes, and I'm going to change the color to color by symmetry operation to see the symmetry equivalent molecules in my structure. Again, I can click more info and see more information about the symmetry. And I can also display the symmetry elements. So to do this, I go to display symmetry elements, and then I see a pop-up where I can tick show symmetry elements. And now we can start to build up a picture of the symmetry inside the structure. So I can see that the pink planes or sheets here are actually glide planes. Just like hydrogen bonds, we could explore symmetry elements in some of the other structures of paracetamol. And don't forget, you can see the space group on the right-hand side. So before we move on to the demo, the final thing we're going to look at is voids. So this time, we're going to change the structure that we're in. So in the structure navigator, we're going to type SAHYIK, and then we'll see this structure. To look at voids, I want to build up the packing in the structure. So I'm going to go to packing and slicing and change how much of the structure I'm visualizing. And then I'm going to go to display voids, and then I have a number of options that I can change, and I can see the volume of void space in the structure, and I can change how I'm going to calculate the void space as well. So you can see one of the ways that I could display my void space in the structure. So there, the basics of what we're going to look at in Mercury, and now we're going to move on to a demo by Ilaria before you get a chance to do a hands-on example. So over to you, Ilaria.
Okay, can you hear me?
Yes.
Perfect. So, and you should also be able to see Mercury on my screen. Perfect, fantastic. So before starting with the demo, just a reminder of some of the basic functionalities. So if we click on the molecule, hold and move it, we are rotating the molecule. If we right click and move up, we're zooming in, and down, we're zooming out. To move the molecule around without rotating, it's Control, click and hold, so we can move the molecule where we want. Otherwise, we can use this command at the top of the window, so we can zoom in and zoom out, move up, down, right, and left. Another thing that we will be using, so it's worth reviewing at the beginning, is changing style. So from here, style, we can select wireframe, for example, capstick, or space fill. So we're going back to the ball and stick option. And a last thing that might be relevant as well is if we want to change the background color, we right click, go to display options, and we can edit by clicking on the color. We select the color that we prefer. Okay. So this should be enough from our first session that we had in November, just to get us started. The structure we want to see today is, okay, we'll insert the ref code together from the structure navigator. It's SALMID02, sorry. Okay, so here it is. If we want to learn more about this molecule thing and this structure, the first thing we can do is go to more info, where we can find all the information. So in structure, for example, we have the ref code, we have the literature reference, we can see the formula, the compound name, synonyms, and the drug bank code. And then we have all the information about this structure specifically. So cell length, cell angles, and so on. And then here we have a number of other information that we will see as we go on later. Okay, so the first thing we want to see is which hydrogen bonds this molecule forms in this specific structure. So if you want to write your guess for how many hydrogen bonds it will form in the chat box, you can do so while I show you how to visualize the hydrogen bonds. So we go in the display options box and we have hydrogen bonds and we just tick it. So you see that, as Susanna showed us before, we have a number of atoms appearing with a ticked line which connects them to the molecule that we have. So these are our hydrogen bonds. So what we can do now, we can click on each of these atoms, and that could have been better. But as you can see, the full molecule appears. So we are expanding the contact. You can also see from the picking mode that our mode is now expand contact. So every time we click on a molecule, on an atom, the full molecule will appear. And the contacts that have been expanded, they become light blue rather than red. So we can go on expanding contacts until we are happy with the network that we're showing. And another thing we can do now, if we don't want to see the contact that we didn't expand, we can delete the hanging contact. So we right click on one of these and go to delete hanging contacts. So they've been removed. So an analysis that we can do now is to see how long these hydrogen bonds are. And the first thing that we study, we can do it by using colors. So first of all, let's change picking mode to pick atoms. And so we want to change the color of the contacts based on the length of the hydrogen bonds. So to do so, we go to Display, Colors, Contacts. We have this pop-up window coming up, Contact Colors, and we select the third option, Color by Distance. We can change this color, we'll see it later, and for now we will apply to all contacts. So as you can see, the contacts change color. I'll zoom in a bit to see a bit more in detail what this means for our structure. So the intramolecular hydrogen bond is colored in yellow, which is the color that it's using for short distance. Then we have some in orange, which is somewhere in between short and medium distance, and then others are in red, which is for medium distance. So the thing we would like to do now is to actually measure this contact, so how long are these hydrogen bonds. So I'll close this window, and from picking mode, I will select measure distances. So as you can probably see now, my arrow became a bit of a shape of a target, right? Bit of a cross. So to measure distances, I will just need to click on any two atoms. In this case, we want to measure this hydrogen bond. So we click on the hydrogen and on the oxygen. And we can see this is 1.7 Armstrong. This is the Armstrong is the unit. We can measure this hydrogen bond, which is in orange, so we expect it to be longer. It is indeed 2 Armstrong, and let's find one that is red, so it should be even longer. Perfect. We can use it to measure any two and any distance between any two atoms, non-bonded or bonded. If we want to delete any of these measurements, we right-click on it and select Delete Measurements. If we want to delete all, you can right-click anywhere and click Clear Measurements. We can also measure angles. So from picking modes, we go to Measure Angles. And again, we have our target shape, cross-shaped pointer. And this time we need to select 3 atoms. So 1, 2, and 3. So of course, in this case, the order is important. And again, any bonded or non-bonded atoms. Maybe you can pick a more relevant example when you do it for your structures. And again, right-click, Clearer Measurement. And since we are seeing how to measure, the next measurement we'll do will be, maybe you can pick mode, Measure Torsions. So this time we will need to select 4 atoms, 1, 2, 3, and 4. So let's see if there's an interesting example to show. 3 and 4. Okay. If we want to see this measurement in a table, we can go to more info and we can see in torsion list. So this is the measurement that we have just taken. In angles and distances, we don't see anything because we cleared the measurement, but if we didn't clear them, they would have been here as well. So let's close this and clear our measurements and go back to pick atoms mode. Okay. The next thing we want to study for this hydrogen bonded network is the pattern that it creates. So what we're going to do is to use graph sets. So for this analysis, I will first of all reset, so it will be easier to visualize each pattern, and I will change the style of the representation to cut sticks. So style, cut stick. Okay, so to show the graph sets, we need to go to calculate. Next thing we want to study for, okay. As you can see, a number of things have happened. So we have a new graph sets tab here at the bottom right, and with a number of descriptors. This first one is highlighted, and a second molecule appeared with some atoms in ball and stick and some letters over the hydrogen bonds. So we're visualizing the R228 pattern, which means it is a ring with 2 acceptors and 2 donors, and the ring is formed of 8 atoms. So here are highlighted the atoms that are involved in this pattern. Then right, and so it's represented with C, with 1 donor, 1 acceptor, and 6 atoms involved in this chain, which are again highlighted with the ball and stick style, 2 to 8, the atoms that are indentation in this case, so we could see this pattern better. This is the intramolecular one, and then you can see combinations of the previous ones as well. So you can explore the other options. Okay, so these were the graph sets. If we reset and go back to our original style, the ball and stick, the next thing we're going to see are the short contacts. So to visualize the short contacts, we click in the display option box, short contacts. And this works exactly like the hydrogen bonds. So clicking on the atoms, it will expand the contacts showing the molecules and then the contacts that it will form. So we can keep expanding as we, oops, don't know why I clicked that, sorry. Can click, keep expanding. Again, we can right click with accuracy and delete the hanging contacts if we're happy with the network that we are showing. The change color, so display colors contacts can be applied to all contacts, so not just for the hydrogen bonds. I want to change the color for long to white because it's going to be clearer with the darker background. We select color by distance and we apply to all contacts. So you can see between the mid and the long range as well. Okay, so far we've seen the short contacts, hydrogen bond network using also the graph set. The next thing we want to see is how to create customized elements for our analysis. In particular, we'll see centroids and planes now. So to do so, I want to show the unit cell of this structure. So display option, I will tick packing. So this is bringing up my unit cell. Let's zoom out a bit. Just a reminder, if you want to edit what you're seeing, calculate packing, you have all the packing and slicing options here to increase what you're seeing. Let's reset to the unit cell now. Okay, so first thing we want to calculate a centroid. So we go to calculate centroids. In this window, we select new centroid, and from the centroid properties pop-up, we see we have three ways to define a centroid. We have picked atom, picked molecule, and ring. So for this example, we're going to keep picked atoms. It means we will need to manually select the atoms we want to calculate the centroid. So we're going to use the lasso option. So from picking mode, we select lasso atoms. We could have also selected from here. And we see that our pointer is now a lasso. So this means we can click, oops, sorry, I was out, click and drag to circle around the atoms that we want to include. So all these atoms have now been selected and also reported in the label. We don't want this long label. We're going to change the name to centroid 1. Centroid 1. We also want to change the color. So we click on the square and select, for example, green. Okay. So now that we have defined it, we click on OK. And we have our centroids that has been created. Let's go back to the pick atom method. So I changed it from this little square here rather than from here, but I could have done it both ways. So I think this centroid is a bit difficult to visualize. So what I'm going to do, I'm going to select it in the centroids list, click edit, and remove the transparency. So it's now much easier to visualize. I close and close this. So next we want to define planes. So we'll go again from calculate, planes. So we define a new plane. Okay, and we see that for the mean planes, we have the same option. So we're gonna try the other two options. We have the same option as the centroids, sorry. So we're gonna try picked molecule to begin with. And let's change the label before. So let's call it plane 1. So with pick molecule, we just click on one atom and it will select the entire molecule. We change the color. In this case, let's go with yellow, for example. Okay. And this will define our plane 1. Okay. Let's create a new plane, which we will call plane 2. And this time, let's select a ring. So in this case, we click on an atom and it will select the entire ring. Perfect. And let's change color just for clarity to, I don't know, this pink, for example. Okay, and okay, so we have plane 1, plane 2, and our centered 1. We can see in more info our centered list and our planes list. Okay, so we can also use these elements to make measurements. So if we go back to picking mode, measure distances, we can measure the distance between the centroid and any other atom, for example. And we can even measure the distance between the centroid, which I've not selected, sorry, centroid and a plane, or any atom and any of the planes. We can also measure the angle between these two planes. So picking mode, measure angles, and we select the planes. So when we select it, we can see that like it has some highlighted dots at the corners. So we selected plane 1, plane 2, and here we can see the angle measured. Okay. So the next part of this demo is gonna go to see symmetry. So let's reset this visualization and go back picking mode, pick atoms. And let's visualize again the packing. So as Susanna showed us earlier, the first thing we can do is to color these molecules by symmetry operation. So we now have our molecules colored by symmetry operation, but what does this mean? To see that, we can go to more info, symmetry operators list. So here we have a list of symmetry operators, descriptors, and detailed descriptors with the color code as well. The next thing we can do is to see the symmetry elements. So we go to display symmetry elements. And now the symmetry elements are displayed here. We can decide what to visualize. So we can, for example, remove the glide planes if we're a bit covering all of the rest, but we could also show them and change the transparency, for example. And we can also, like, for example, the inversion, we can remove them or show them or change the size to make them more visible. So I think this all for this demo, but it would be interesting if you want to see other polymers, for example, what changes between the hydrogen bond networks and between the symmetry elements. So I think this brings me to the end of the demo.